Good morning. Let's now talk about two types of diffractions or two classifications, as we can say. They are Fraunhofer diffraction and Fresnel diffraction. In Fraunhofer diffraction, when both incident and diffracted wavefronts are plane wavefronts, we call it Fraunhofer diffraction. Then it is an example of a far field sort of source. Then the Fresnel diffraction is applicable when the wavefront curvature is significant. We have to really take into account the curvature of the wavefront. This normally happens if you have a point source which is very close to the aperture or slit. Maybe you can make a more quantitative classification. If you look at the picture, we have a slit which has a width of delta and I have a source which is rough at a distance of, let me just see, at a distance of r prime from the slit. Then I have a point of interest where we want to see the profile, or that is P. It's a distance r from the slit. Now we just define certain variables or certain dimensions, distance to the source, the straight distance or perpendicular distance from this slit to the source is d prime. Then that of the observation point is d. Then the observation point, the height to the bottom of the slit is h. Then to the height to the bottom of the slit of the source to the bottom of the slit is h prime. Okay. Now, what we are interested is, okay, here we have the light travels a distance r plus r prime from the source to the observation point at one end of the aperture. Now, on the other end, let's say the distances are r1 prime and r1. Therefore, we are, okay, the interference or we are concerned or we are interested in the difference between the two, okay, that is r1 plus r1 prime minus r prime plus r. Let's call it something called, okay, that is the path difference between the two extreme waves. Purely from the geometry of the whole thing, we can find expressions for r plus r prime and r1 plus r1 prime. Okay. You may consider the two triangles. One is this one here, and the other is this one here, to find r and r plus r prime. Now we can use another two triangles like this one for R1 prime and this triangle here for R2 prime. Sorry, R1. Okay, if you do that, this is the distance. This is h plus delta all square plus d square, that is h plus delta, that is R1 R1. This quantity here is R1. This quantity here is R1 prime, and this quantity here is R, and I think that is R prime, and this is R. Okay, this is R plus R1 minus R plus R. Okay. Now you do some simple rearrangements. That means I have to send you the notes, or it is actually simple. If you just take uh, D out, the first thing that you can do. Okay, okay. Let me see whether I can do it here. If you from the first one, if you take D square out, that means D out uh, outside the square bracket, that is 1 plus h plus delta over d whole square. Here we have d1 or d prime, that is 1 plus h prime plus delta by d prime whole square minus, again you take d prime, okay, d prime out, that is 1 plus h prime square over d prime square, h prime, not one, h1, plus minus d times 1 plus h square minus d square. These are the 4 times. And now if you simply take the first term in this series expansion, that is 1 plus x raised to half, where x is small, uh, or any value. If, in fact, that is d times 1 plus half h plus delta over d whole square plus, okay, you have to add the other terms, plus the second term d prime. I'm not making any approximations. I just use I just write only the first term, but you have the other terms included here. And because that's going to be higher order terms, maybe we will take something that is important. Okay, what we are interested is in the first two terms actually. That is times 1 plus h prime plus over delta d prime half all square plus etc. and plus d prime times 1 plus half h prime square over d prime square plus etc. Okay, actually I should have put this bracket here. That would be better. Plus or minus. Okay, this is minus d times 1 plus half s square over d square plus. Okay, and that means if you rearrange the terms, what will you get? Here we have a square term in delta square. Here you have square term delta, and the coefficients will be these two, because there is a d square in the denominator, and d times d square will give you d, and here we have, okay, that's something that's proportional to delta. That actually comes from the expansion here, that is s square plus 2s delta plus delta square. Okay. And if you write these expressions, the first two terms, there will be some cancellations. Minus d prime here and plus d prime here will cancel out here, right? And d here and d here will cancel out, and if you rearrange the whole thing, you can get something like this. You can express it in terms of a power series which is in delta, that is dimension of the slit. Now the second term here represents the curvature of the wavefront, and the wave is effectively plane over the aperture if this quantity here is much less than lambda, and that becomes the criterion for conditions for Fraunhofer diffraction. If this condition is not met, then the curvature is important, and we call it Fresnel diffraction. Now we start with the Fraunhofer diffraction patterns. Now we would like to express the field distribution at the observation point, and also the intensity UP and IP, the intensity at that point, intensity distribution at that point. And what we know about Fraunhofer diffraction, this is Fraunhofer diffraction, and what we know about Fraunhofer diffraction is the wavefronts are parallel at the slit, or the curvature is negligible, they are plane wavefronts. How do you make a plane wavefront? Of course, if you have a source that is too far away, like the sun, you can say that whatever is coming in is as a plane wavefront. The curvature is so negligible that you can consider it as a plane wave. But you can also do a collimation of the lens, and if you have a collimating lens with focal length f, and you know these things, and if you keep it at a distance of f away from the source, from the point source, whatever is coming out will be a parallel beam of light. That means at the slit, these are plane wavefronts. Or in other words, there is we have, for when you consider the Fresnel-Kirchhoff formula, we had something called an obliquity factor that depends on the angle between the normal to the surface and the vector here. I think we have taken it as R, and here we have taken it as S, and it was we had a factor that include cos ns and cos n r minus cos, and we called it an obligate factor. But since these are parallel wavefronts or plane wavefronts, these normal and the radius vectors at this point can be considered parallel, and therefore or constant, then we can make certain assumptions. And in this case, in this picture, we can see that the incident and the diffracted wavefronts are strictly plane. They both are plane, and this imaging lens or focusing lens here, this guy here, will image the diffraction pattern at the screen or focus the diffraction pattern at an external screen at distance p or place that going through the point P. Let's revise or go back to the Fraunhofer integral formula that was about this one. We had an area integration. The area integration was over the aperture. We had an aperture like this, a slit, which is basically something like this with a length L and some A as the height. Then this integral, this whole integral is done over the whole area of this area. We have seen it in the last class, and therefore this is essentially the area. Now, with the plane wavefronts, we can make about 3 assumptions to make life easier. Here, as I said, the obligate factor is a constant over the aperture and can be taken out of the integral. You take this factor out, and therefore the integral becomes integral. Okay, this constant factor is here. This constant was already there in the Fraunhofer integral. Then we have the area integral of e to the power I k r plus s. Okay, in the previous r and s was okay. This is source. Here we have taken it as r, and here you take it as s. Okay, this e to the power I k r plus s. Now the second assumption is e to the power I k s over s is nearly constant and can be taken out of the integral, because here this has to be symmetric for us to be able to make able to make use of a lens to make it collimated and parallel to the slit, or to make it plane a plane wavefront, and therefore this is nearly constant, and therefore here s is going to be a constant. Not really a constant, but it can be, since the slit is normally small, you can take it or you can assume that okay, if this is S0, this is going to be S0 plus delta S, and if that delta is a constant, which means the e to the power IKS over S over the aperture is going to be a constant. And also the wavefront, I can say it's not going to be a spherical wavefront, and therefore e to the power I k s over s is a constant. Especially since this is a plane wavefront. E to the power I k s over s is nearly a constant. You take that out. What remains is in the integral, inside the integral is e to the power I k r over r. Now we take a final assumption that the variation with respect to r comes from two factors. This is 1 by r and e to the power I k over. And since and this is a rapidly varying function, and this is more gradual in the present situation, and therefore 1 by e to the power I k r contributes more towards the variation in the whole time here, and therefore we are going to replace r by its mean value. Okay, let's say that is r0, and can be taken out of the integral. And therefore we have a large number of terms taken out of the integral. What is left is e to the power I k r by r. What we have to do is to integrate this. Yeah, it is, in most cases it's relatively straightforward to integrate that. And this ds here, as you remember, it is the area. It represents the area, or dA is the area element of the in the aperture. And therefore if you consider everything as a constant, then you replace c up with the big constant c, and this is what you would get. Let's now find look at an example of single slit. Here we have two parallel rays, or a parallel many parallel rays coming into the slit. The slit itself is of height b and length l. That is, it is like rectangular slit. Let's say this is L and this is B. But for convenience, we take it the height as minus b by 2 to plus b by 2, just to make the integration and limit application of limits easier. How will you integrate this over an area? You consider a small element, area element, and if you take this direction as y, then the area element will be L dy, isn't it? L dy. And also, considering the geometry, these waves, two waves, are going to go to a point where it is P, and the difference in length, okay, from here it is the same to the point P, and therefore the difference is y sine theta, or R is R0 plus y sine theta. R0 is the mean distance. If you take something from the center, R0, this is your R0, distance from this to the point P, that becomes R0. From the center, let's say the center of the aperture slit. Then R is R0 plus y sine theta. Simply substitute it into into this equation, C integral e to the power I k r dx. which we have just done with certain assumptions of a plane wavefront, and therefore just substitute for the values. R is R0 plus R0 plus ky sin theta, y sin theta, and therefore you can take e to the power I k R0 outside, and this is dI is L dy, and therefore your integration is over y. Now e to the power I ky is cos ky sin theta plus I sin ky sin theta. Just simply do the integration, and because it is a symmetric b by 2 to minus b by 2 to plus b by 2 integral, both of them, you apply the limits, you get something like this. When it's in the lower limit, it's minus kb by 2, sin minus kb by 2 will become minus kb, minus and minus will become plus, and therefore you get this. But here it remains negative, and therefore this thing becomes 0. Whatever you get here is whatever is left is this one. But since we want to make this and the denominator the same, simply multiply the numerator and denominator by b. You take this 2 to the denominator, and therefore you get something like this. This is like sin theta over theta, or let's say sin beta over beta. It's a well-known function which is called a sinc function, and therefore this is what you get. This becomes some c e to the power I k r0 L b over sin beta over beta, where beta is half kb sin theta, and c prime is this one. Actually this is okay, this is sin beta over beta, and if you take the intensity, it is the amplitude square, that is sin beta over beta the whole square, with multiplied by I0. I0 is just the modulus square of this one, that is CLB the whole square, that is the radiance at theta equal to 0. And the first max minima occurs at beta equal to pi. At beta equal to pi, this becomes 0, and or half kb sin theta equal to pi, or sin theta equal to 2. Okay, that is the condition for first minima. And if you plot the intensity, the normalized intensity, you get something like this. And it's a symmetric function, symmetric intensity distribution with a central peak and many side lobes. Okay. If you look at the screen, the central width is much higher compared to the other ones, and also it is more intense. Okay, this is as a, okay, this picture here is a realistic sort of thing, and therefore it is the maximum intensity at the center, and with many secondary maximas at regular intervals, and therefore the intensity distribution of diffraction from a rectangular slit is a sinc square function. Sinc square function, or it varies as sine beta or beta. Remember, intensity is something that you can measure. That's why we concentrate on intensity. This expression here may be useful when you want to try and consider Fourier optics. Essentially, what you get here is a Fourier transform of the aperture function. Aperture function here is a sort of square wave or a step function, not step function. And therefore a Fourier transform of this is a sinc square function. That's exactly what you see here. Okay, and we'll see the examples of circular apertures and double slit cases in the next class. Thank you.